Today's lesson is on properties of rational functions. And these properties are all of the properties and key parts you need to graph the function, which we will do next class. We're going to go through the domain, intercepts, and asymptotes. This is quite a long lesson, so I'm going to skip through some of the examples. You can find any example that I skip on my answer key posted on my website. But to start off with, we just need to review what a rational function is. And a rational function is defined as the quotient of polynomials in which the denominator has a degree of at least 1. So that means you have a polynomial in both the numerator and the denominator. So an example of this could be y equals 3 over x. That's a very simple rational function. We could have 2x plus 1 over x plus 5. That's another example. We could have something a little more complex, x squared minus 1 over x squared plus 2x minus 3, and so on. So you have a polynomial in both the numerator and the denominator. The first key topic we're going to go over is the domain. Again, these are all things we need to know for graphing. So to start with the domain, just a refresher, the domain is the set of input values. It's all real numbers except those values of which the denominator equals 0. So we need to find these values and then get rid of them. The steps are first to set the denominator equal to 0. Then you solve for the variable. And then the solutions found in step 2 are the values you must omit from the domain. We have already done this year, so you might remember doing this at some point. Whatever you find for values, the values that you have to omit must be written in interval notation. Starting with number 1, our fraction is 2x minus 5 over x plus 4. At this point, we don't care about the numerator. We just look at x plus 4. We know that the denominator cannot equal 0. Again, we have done this, so hopefully this is just a refresher. Subtract 4. X cannot equal negative 4. That's telling us that the domain of this equation, the domain of the entire rational function, is any number except for negative 4. And it's written as negative infinity to negative 4 with a union negative 4 to positive infinity. For the second example, we have 3 over x squared minus 5x minus 14. This denominator is going to have to be factored in order to be set equal to 0. And this factors to x minus 7 times x plus 2. Negative 7 times positive 2 is equal to negative 14. Negative 7 plus 2 is equal to negative 5. This tells us that x cannot equal 7 and x cannot equal negative 2. The domain is from negative infinity to negative 2, union negative 2 to 7, union 7 to positive infinity. Next, we're going to look at following the steps for the x-intercept. So to find the x-intercept, you need to factor the numerator and the denominator, and then you need to eliminate any common factors. That's very important in step 1. After you eliminate any common factors, you set the remaining numerator equal to 0. And after you do that, you solve for the variable. In number 1, if we factor both the numerator and the denominator, all we can factor is a 2 out of the numerator, leaving us with x plus 3, divided by x plus 2. So in this case, there are no common factors. And to find the x-intercept, you just take the numerator and you set that equal to 0. So we get x equals -3. As an x-intercept, we would write this as -3, 0. You can have multiple x-intercepts. For number 2, our numerator has to be factored. We have to eliminate any common factors between the numerator and the denominator, and then we need to set the numerator equal to 0. Actually, in this case, our denominator can be factored too. Missed that one. The numerator, we can take out an x, left over x squared plus x minus 2, divided by the denominator, which we can factor out of 4, left over is x minus 1. The numerator can be factored again. We can factor x squared plus x minus 2 to x times x plus 2 times x minus 1, all divided by 4 times x minus 1. All right, in this example, we do have a common factor. We can eliminate x minus 1. That leaves us with x times x plus 2 divided by 4. And at this point, you take your remaining numerator, you set this equal to 0, and you set each factor equal to 0. We have a factor of x equals 0, that's this factor, and we have a factor of x equals -2. So in this example, our x-intercepts are at -2, 0, and 0, 0. Next is our y-intercept. Finding the y-intercept should be something you remember from the past. In this case, you set the variable equal to 0, and then you solve the function. In this case, you'd be solving for y. I know sometimes it says f of x, but f of x or y are the same thing. I'm only going to go over the first example here. I think that finding the y-intercept is something we've done quite a bit this year. If we substitute 0 in for x, so setting the variable equal to 0, we have 0 squared minus 3 times 0 minus 10 divided by 0 minus 3. And again, I substituted 0 in wherever I previously had a variable. This simplifies to 0 minus 10 over 0 minus 3, which is -3. So in this example, our y-intercept is at 0, 10 over 3. I can just tell you quickly that the y-intercept for number 2, which I'm not going to do out, but I already know it's 0, 1. You can probably tell that just as fast as I'm telling you this, if you understand what you're doing. So 0, 1 is the solution. Next, we're going to talk about continuous versus discontinuous graphs, which leads us into holes and vertical asymptotes. So continuous graphs are graphs that have no jumps, breaks, or holes. You can draw the graph without the pencil ever leaving your paper. So for example, if I was to draw a continuous graph, it could be something like this. You can have multiple curves, but it goes on forever. So that's obviously quite a detailed graph. You have multiple turning points, but it never stops or makes a jump. So your pencil never left the paper when you're drawing it. A discontinuous graph is the opposite. So it's when your graph has different parts to it. So this graph has an endpoint, different endpoints, and starting points. When we graph rational functions, we have horizontal or oblique asymptotes, which will also, I guess I should add horizontal, vertical, or oblique asymptotes, which will also create a jump in the graph or a break in the graph. So looking at holes to start with, all of these kind of run together. So starting with holes. Holes are points of discontinuity or removable discontinuities. They're moments within a function that are undefined and appear as a break or a hole in the graph. So when you're graphing them, they are graphed just like they sound. If I'm graphing this line, which is just going to be what appears to be a straight line with a hole in the graph, I stop graphing, I draw an open circle to indicate a hole, and then the line continues. So this right here is considered a hole. All right, holes are produced by factors that are common to the numerator and the denominator. The x-coordinate of the hole is found by setting the common factor equal to 0. So that means you must factor both your numerator and your denominator, set the common factor equal to 0, and solve. The y-coordinate of the hole is found by substituting the x-coordinate back into the simplified function. Number 1, hopefully you can tell that number 1 is not going to have any common factors. If it doesn't have any common factors, then there are no holes. I'll quickly write this one out, but I do want to explain more on number 2. Number 1 factors to x minus 5 divided by x plus 1 times x minus 1. And there are no common factors. When there are no common factors, there are no holes. Which leads us to number 2. Number 2 is x squared minus 3x minus 4 divided by x minus 4. When I factor my numerator, I factor this to x minus 4 times x plus 1. All right, this is because negative 4 times 1 multiplies to negative 4, and negative 4 plus 1 adds to negative 3. This is divided by x minus 4. So now I'm going to indicate that my common factor cancels of x minus 4, but then I'm also going to write my simplified function. My simplified function is x plus 1 in the numerator divided by 1. And it's divided by 1 because we divided out the common factor. Next to this, I'm just going to put in parentheses that this is my simplified function. Now I'm going to take my common factor and I'm going to set it equal to 0. So I have x minus 4 equals 0. This tells me that x equals 4. Then I'm going to substitute x equals 4 back into the simplified function, and I'm going to solve for y. Okay, so once we substitute this back into y, we are actually substituting x equals 4 back into the simplified function. So make sure you get that correct as far as which one you're substituting it back into. That means y is equal to 4 plus 1 over 1, which is just y equals 5. Okay, again, you're substituting in from the simplified function. Super important that you get that one. So once you get to this point, you know your x coordinate is 4, you know your y coordinate is 5. That tells you that you have a hole at x coordinate 4, y coordinate 5. Here's your answer. So vertical asymptotes are a line that a curve approaches as it heads towards infinity. You have to find vertical asymptotes after you find the holes because they are found after you simplify or after you take out the hole. You can see that a vertical asymptote is a line that the graph approaches and never touches or crosses. Again, we have talked about these this year, we just have not found them. So here we are actually calculating what they are. Again, it's after you determine the holes. So after you determine the holes, you set the denominator equal to 0 and you solve. Number 1, we don't have any common factors, so we can indicate that there are no holes. And then from there, if we set each denominator factor equal to 0, we have x equals positive 1 and x equals negative 3. These are your asymptotes. So we have two asymptotes here. I'm going to label them VA for vertical asymptote, and the vertical asymptotes are at these two values of x equals 1 and x equals negative 3. Next class, once we start to graph, you will graph a dashed line at each one of those values. For number 2, we need to factor both the numerator and the denominator. The numerator factors to x plus 1 times x minus 1. The denominator cannot be factored, it is just x plus 1. Here we can see that we have a common factor of x plus 1, so we can calculate the whole. Before I actually calculate the whole, I'm going to write my simplified expression as x minus 1. That's technically x minus 1 over 1, but x minus 1 works. It is the same thing. All right, so the whole is found by the x coordinate of setting the common factor of x plus 1 equal to 0. The x coordinate is negative 1. The y coordinate is found by substituting x back into the simplified function. When we do that, we have y equals negative 1 minus 1, or y equals negative 2. That's the y coordinate of your whole. So this tells us that we have a whole at negative 1 comma negative 2. Because we don't have any common factors, because we don't have any denominator left after we simplify, there's no denominator to set equal to 0. Therefore, we would say that there are no vertical asymptotes. So in this question, you're asked to find the horizontal asymptotes and the holes. We have a hole. We do not have a vertical asymptote. And that is exactly what you would indicate. No vertical asymptote. And that's because there is no denominator after you simplify from the hole. And the last thing we're going to cover today is the horizontal asymptote. So the horizontal asymptote is one of 3 cases. So write these down as I go over them. The first case is going to be if the degree of the numerator is larger than the degree of the denominator. In this case, you have no horizontal asymptote. So an example of this could be 3 is greater than 2. For the second potential answer, if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is always at the line y equals 0. And for the third potential answer, if the degree of the numerator is equal to the degree of the denominator, then you set up a fraction, and the horizontal asymptote is equal to the leading coefficient of the numerator divided by the leading coefficient of the denominator. Your solution has to fall within one of these 3. So obviously this year's open notes, make sure you just reference these 3 cases and match which one works for your problem. If we look at number 1, y is equal to 2x over x minus 3. The degree of the numerator is x to the first power, degree of the denominator is x to the first power. So this actually matches number 3 up above. The degree of the numerator is equal to the degree of the denominator. That means we set up a fraction, leading coefficient over leading coefficient. So the numerator has a leading coefficient of 2. The denominator would have a leading coefficient of 1, but we just don't write that. I just added it in. So the horizontal asymptote is at y equals 2 over 1 or y equals 2. And again, that's the leading coefficients just set up as a fraction. Number 2 has a degree of 1 in the numerator, degree of 2 in the numerator and a degree of 1 in the denominator. This would match the first case, so the degree of the numerator is larger than the degree of the denominator. 2 is larger than 1. Therefore, our answer would be no horizontal asymptote. And that's it. There's nothing else to find, it's just no horizontal asymptote. For the on your own section, please try to complete these by yourself. Follow all the directions individually. So the directions for the domain, directions for x-intercept, y-intercept, vertical, and horizontal asymptote. Here's my answer here, where you can also find it on my website underneath the answer key. Last, we need to talk about oblique asymptotes. And oblique asymptotes only occur when there is no horizontal asymptote. So when there's no horizontal asymptote, that means there will be an oblique asymptote, at least for the examples that we do. So right here you see the formal definition of an oblique asymptote, but basically, if we zoom in on this graph, if the numerator has a degree that is 1 more than the denominator, so the degree of the numerator, again, is 1 more than the degree of the denominator, then you are going to have an oblique asymptote. Okay, you might want to pause this to copy this down. I'm going to scroll down to the next example. So for the first example, we have y is equal to 3x cubed plus 2 divided by x squared minus x minus 7. So you can clearly see that the exponent of the numerator is 3, the exponent of the denominator is 2. When this happens, you set up a long division or synthetic division, but most of the time it has to be long division because of the functions that you're working with. You set up a long division problem. Whatever's in the numerator is going to go under your long division sign. Make sure you include all terms. So our numerator is 3x cubed. We have plus 0x squared plus 0x plus 2. That's our numerator. Our denominator becomes our divisor. That goes outside of your long division sign. And then you divide out the function. So we have our first term, 3x cubed divided by x squared, just like previous long division problems that we've done. When we do this, we're left with 3x. That's our first term. 3x times all terms, we have 3x times x squared, which is 3x squared, no, 3x cubed. 3x times negative x is negative 3x squared, and 3x times negative 7 is negative 21x. We are subtracting all terms. 3x cubed minus 3x cubed is 0. 0 minus negative 3 is positive 3x squared. And 0 minus negative 21 is positive 21x. Bring down the 2. Repeat the process. Three x squared divided by x squared is 3 for your final term of your quotient, of which you multiply out to all terms in the divisor. This gives you 3 times x squared, or 3x squared. 3 times negative x, negative 3x, minus 21. We're subtracting both terms. Sorry, we're subtracting all 3 terms. 21 minus negative 3 is the same as adding, so that would be plus 24x. 2 minus negative 21 is the same thing as adding. 2 plus 21 is 23. All right, so when you are finding the oblique asymptote, your oblique asymptote is only the quotient. So I'm going to label this as the remainder. But we actually don't need it. So previously we've used this. Now we are only looking at the quotient. Oops. So if we were to label our oblique asymptote, first of all, anytime you have an oblique asymptote, you instantly have no horizontal asymptote. So I'm going to include that in this answer. No horizontal asymptote. And then oblique asymptote, we're going to write it as a function. It's always in slope-intercept form. It's this function. It's your quotient. Forget about the remainder. The remainder is not part of your answer. So y is equal to 3x plus 3. This is your answer. That's it. Just the quotient. Of course, we have a remainder. We do not want to use it as part of our answer. Okay, for number 2, same thing. Let's compare our exponents. We have 2x cubed divided by x squared plus x minus 12. So I'm going to get started with this one, and then you can just watch me finish the rest of it. But whatever your numerator is, it goes underneath your division symbol. We have 2x cubed plus 0x squared plus 0x plus 0. And our divisor is x squared plus x minus 12. Okay, so if you just follow along, you can watch me do the rest of this problem.